haven't given you some basic idea of conduction, especially one that involves steady state and one dimensional, predominantly one dimensional. It's important to understand that there is another mode of heat transfer. See, there is a hot surface. Say this is a hot surface at temperature T hot. Right? At temperature T hot. This is becoming a hot surface, for example, right now. Okay? And there is a fluid flowing over it. Let's say there is a fluid flowing over it. There is fluid that's made to flow over the surface. Then it's found that the temperature of this decreases. It becomes cooler. Temperature of this becomes less. In this case, the molecules that flow over this and that come in contact with this communicate heat. There is transfer of heat and they carry away the heat from the surface. They carry away the heat from the surface. Now, this mode of heat transfer between the fluid and the surface, in this case, for example, is because of a bodily flow of one thing, right? There is a flow involved here. There is a bodily flow of molecules somewhere, right? This mode of heat transfer is convection. This mode of heat transfer is convection. It's because of the small contact period that the molecules have with the surface that they carry away the heat. Now, this mode of heat transfer is very complicated, and that's the reason they have chosen to not keep it in your IIT JEE syllabus. The model associated, essentially, then at any given instant of time, say this is the temperature of the fluid flowing over it, Tc is the temperature of the fluid flowing over it, then the watts per meter squared associated with it, the watts per meter squared associated with this is going to be given by some H into Th minus Tc, Th minus Tc at any given instant of time. Tc is the temperature of the fluid flowing over it, and Th is the temperature of the hot surface. Now the problem is, it looks so easy, and why is it not kept in the syllabus, right? The problem is obtaining this value of H. It's the biggest problem in heat transfer. Biggest problem in heat transfer. This is called convective heat transfer coefficient. And you know what are the factors that it can depend on? One, the thermal property of the surface and the thermal property of the fluid. That's one thing. The velocity of the fluid, you realize that it will also depend on the velocity of the fluid. And in fact, it will also depend on Th. It will depend on Th as well as Tc. Now, Tc can be assumed to be practically constant. Let's say, there is a huge volume that I'm making to flow, but Th can't be constant, right? This is a huge mass whose temperature does not vary, but this Th will certainly vary, and this H actually will vary with Th. Will vary with Th. This problem of convective heat transfer is very, very involved, very involved. I mean, like I said, it will depend on all the properties of this fluid. Yes, it will depend on the thermal properties as well as other properties of this fluid, everything. So then it's really complicated. It's really complicated. But to tell you honestly, if at any point of time you have to deal with heat transfer, to imagine that there is only going to be conduction in a given situation is utopian. there is simultaneous presence of conduction and convection for sure. Yes, radiation also, but very rarely would you find a situation in which there is only conduction. It's only for an exam that we give only conduction. But a real life problem involves convection, it involves conduction, and it involves radiation as well, right? So this model is not dealt with at this level, but then those of you who go on to study, become core mechanical engineers doing core simulation, a typical heat transfer problem, if you have to model a furnace, it will involve like 1500 differential equations with 1100 boundary conditions and all partial differential equations. They can't be solved with the help of the 6 forms of differential equations that you have learnt at this level, right? The solution to those differential equations are done using either with what's called finite element methods or numerically. They are done numerically, so they are very, very intricate, and for each of those differential equations you will have to devise a new technique of solving that differential equation. It will not be there in Tata McGraw-Hill books, okay, or Cengage. So in any case, just a passing reference to convection, but we need to know a little bit about radiation. Again, that too, the core radiation, radiative heat transfer is very, very involved, although less involved than convective heat transfer. Yet, some of the approximations that you learn with radiative heat transfer are within the scope, purview and reach of students at this level. So, just to take you very briskly past the rudiments of another mode of heat transfer, which is radiation. Now, both conduction and convection were modes of heat transfer that took place in presence of material media, right? A material medium was required for this mode of heat transfer. However, you'll find, let's say, that if there is this hot surface, TH, right, and in an enclosure, which is a cold enclosure, temperature TC, right, and there was vacuum here. Now, if there was no material medium between the two, you couldn't have had conduction, you couldn't have had convection. Yet you find that the temperature of this decreases and the temperature of this increases. That means there must have been a third mode of heat transfer which does not require for its propagation a material medium, and that mode of heat transfer is radiation. Now, essentially, there is an ideal radiator. When we talk of these radiations, these are essentially electromagnetic waves. When I talk of these radiations, thermal radiations, these are electromagnetic waves. So, we'll have all properties of electromagnetic waves, right? Now, however, they can get attenuated. The signals, these thermal waves could lose intensity. If they travel through a material medium, they can lose intensity. There could be a material medium which is not transparent to their propagation. See, vacuum is transparent to propagation of electromagnetic waves. It will not attenuate or dilute electromagnetic signal. But there could be a medium, let's say there is water through which an electromagnetic wave travels, thermal radiation in the form of electromagnetic wave, then water will attenuate and dilute the intensity of the electromagnetic waves, because it's going to absorb some of the electromagnetic waves, and the signals, the thermal signals, will become weaker as they propagate along the line of propagation. Now, there is what's called an ideal radiator if it's at temperature T. When I talk of thermal radiations, we now all of a sudden move not to degree centigrade but to degree Kelvin. We now talk in terms of degree Kelvin, and if there is this surface at temperature T, then it's an ideal surface if the watts per meter squared, the Q, that is the watts per meter squared that it radiates, we'll call it E, let me call it E, is some constant sigma into the fourth power of the temperature. This is the radiation model for an ideal surface, where the watts per meter squared is proportional to the fourth power of the absolute temperature, and this sigma is a constant and is called Stefan-Boltzmann constant. And is a value 5.67 into 10 to power minus 8 watts per meter squared, degree Kelvin to power 4, watts per meter squared per degree Kelvin to power 4. That's Stefan-Boltzmann constant, and this is called Stefan's law. In fact, it's Stefan-Boltzmann law. Stefan does not matter. Sit down. Now, to tell you again, this is very, very involved. I mean, this they have obtained by experiment. Not only by experiment, the check was with experiment, but in this case, it was not purely empirical. There is a proof which is like huge, very huge proof of this. We can't spend time on this, but if you like, I can give you material which you can read and get. But it's very involved proof of this. It's a very involved proof of this. The fourth power of absolute. No, it's enough. The maths that you know is enough to understand the proof of this. But it's very involved. Now, so this is the heat flux. This is the heat flux through a surface in the form of radiation, which is proportional to the fourth power, and bodies that exactly subscribe to this are called perfectly black bodies. This is the emission in the form of thermal radiations. And if they are in the form of electromagnetic waves, then they have a certain wavelength. This energy has a certain wavelength. In fact, this total amount of energy, these many watts per meter squared, contains all possible wavelengths. Starting from lambda equal to 0 to lambda equal to infinity. This total amount of watts per meter squared that's emitted from the surface contains all possible wavelengths starting from lambda equal to 0 to lambda equal to infinity. So there is a thermal spectrum starting from lambda equal to 0 to lambda equal to infinity. All possible wavelengths are there. Yes, some of them are in the visible range. Roughly around close to 0.4 to 0.7 microns is actually the thermal radiation. However, real bodies, this is only a perfectly black body. Real bodies, when they are at absolute temperature T, then the radiations that they emit would not be sigma T to power 4, would be some epsilon sigma T to power 4. Where epsilon is the emissivity of a real body, and it lies between 0 and 1. Epsilon equal to 1 for a perfectly black body. Emissivity means what fraction of the perfectly black body signal is being emitted at the same temperature. So if this is 0.5, that means 50% of a perfectly black body is what it emits. This is the model for a perfectly black body, but for a real body, it's going to be epsilon times what it is for a perfectly black body, right? essentially at a given temperature T, the emission characteristics as a function of the wavelength, Like I said, all wavelengths are included in this. All possible wavelengths are included in this, right? So as a function of wavelength, this is how this is called emissive power. At temperature T, as a function of wavelength lambda, this is what it really means is this is like watts per meter squared per unit wavelength. Let me explain this to you, what this E lambda actually means. This is at a temperature T where watts per meter squared per unit wavelength for various values of lambda. So in this case, say I have lambda equal to 0, lambda very large, and there is an intermediate lambda, and I take so this is a continuous spectrum. When a black body emits radiations, it emits radiations of all possible wavelengths, lambda equal to 0 to lambda equal to infinity. If I take a certain wavelength lambda, then there is a small band around this, lambda plus d lambda is a small band around this. Now when I say the emission at lambda is E lambda, what it really means is the watts per meter squared per unit wavelength surrounding lambda. Watts per meter squared per unit wavelength surrounding lambda is E lambda. What it means is that over this d lambda, what's the energy that is radiated? That means watts per meter squared. How much watts per meter squared is emitted over this wavelength lambda to lambda plus d lambda? It's going to be E lambda into d lambda. You know what I'm saying? When I say the watts per meter squared per unit wavelength at lambda is E lambda per unit wavelength surrounding lambda. That means at lambda, if it's E lambda, then the total energy contained in a spectrum from lambda to lambda plus d lambda, this is energy per unit lambda. So over d lambda, this would be the energy, right? So this is E lambda energy watts per meter squared per unit lambda per unit wavelength surrounding a certain lambda. That's what it means. This is the energy over this from lambda to lambda plus d lambda. This is the energy. These many watts per meter squared, right? So the total area under this curve, lambda equal to 0 to infinity, the total area under this curve, E lambda, d lambda, would be sigma T to power 4, absolutely would be. This is the total energy, watts per meter squared, which is sigma. This will be proportional to the fourth power of the temperature. This will be proportional to the fourth power of the temperature. The area under this bell-shaped curve is going to be sigma T to power 4. Right? Now, at lower temperature, now E lambda peaks at a certain lambda. At lambda m, it peaks. That means there is maximum energy in and around wavelengths lambda. That means close to lambda m. The energy, the watts per meter squared is maximum. That means the intensity is maximum around some wavelength lambda m, right? At smaller temperatures, so this is, let's say, T1, at temperature T1. Okay. If I increase the temperature of that black body, then the variation could be this. This would be a lower curve for T2 less than T1. Sorry. In a general sense, this is T2 less than T1. And this varies. This peaks at some lambda m prime. Whereas this peaks at lambda m. As you go on decreasing the temperature, then at higher and higher wavelengths, do you find peaks of E lambda. That means if you know what I'm saying? If you decrease the temperature, then the maximum intensity is obtained for higher and higher wavelengths. That means for longer wavelengths, You know what I'm saying? At smaller temperatures, higher wavelengths are preferred for higher intensities. The maximum intensity is obtained at higher values of lambda for lower temperatures, In fact, lambda m is the wavelength at which the intensity peaks, right? So if a certain radiation takes place at temperature T, let's say this is at temperature T, and its intensity peaks at lambda m, then it's found that lambda m into T is a constant. Which means lambda m into T1 must be lambda prime m into T2. And this constant is called Wien's constant. And this law is called Wien's displacement law. This is called Wien's displacement law. Lambda m into T equal to constant, and its value is found to be 0.282 centimeter Kelvin. 0.282 centimeter Kelvin. Sometimes they use this as 0.3, sometimes they use it as 0.29, based on the problem. Whatever is more convenient in terms of calculation, some 0.3, 0.29, etc. So this is Wien's constant, 0.282. Again, there is a formal mathematical proof of this. Just in case you want to know, I can share the material with you. But this is not just purely experimental. It has a proper formal mathematical proof, right? Lambda m into T equal to, T of course, remember, must be in Kelvin. T must be in Kelvin. So this is Wien's displacement law. In fact, this is the emission characteristics of. Sometimes, let me just tell you one passing reference. It's important to know this. Can I wipe this off? Can I just wipe this off? I know it's a little hot. We're talking of radiation. Had to be a little hot, right? Even at the same temperature, these emission characteristics are different for different bodies. In fact, they are not only emission characteristics, they are also absorption characteristics. You know this E equal to sigma T to power 4? Where T is the temperature of the body and sigma T to power 4 is the watts per meter squared that is radiated. In contrast, if T is the temperature of the surroundings, if there is a body, let's say a perfectly black body, and T is the temperature of the surroundings, then it will absorb heat in the form of radiation. Which will also be of the form sigma T to power 4, So this is not only the emission characteristics, the sigma T to power 4 is also the absorption characteristics. Absorption also takes place commensurate with sigma T to power 4. So if there is a body, let's say at temperature T1, then there would be simultaneous emission as well as, let's say a perfectly black body, a simultaneous emission as well as absorption. So the emission here would be sigma T1 to power 4 watts per meter squared. The absorption here is going to be sigma T to power 4 watts per meter squared. Right? So if this is larger than this, there would be emission. There would be net emission. And if there is net emission, it will lead to cooling. If T1 is bigger than T, it will lead to cooling, net cooling. Simultaneous emission as well as absorption takes place. That is the important thing. So whatever I drew in terms of that bell curve, which was an emission characteristics, is also the absorption characteristic for a given material at temperature T. You know, when we, in paper mills, do you know how the whole thing functions? The cooling, there is this wet paper coming down the rolls, and it has to be dried. Now, the drying of that paper does not take place by exposing it to 2000 degrees centigrade and melting it away to glory, right? There is soft heating. Again, you can't expose that paper to fluid at higher temperature or fluid at lower temperature and do things, right? You can't expose it to fluid. You can't do a conduction heat transfer. You can't do a convection heat transfer. So to dry that up, what's actually done is this radiative heat transfer. There are hot radiant tubes inside a furnace, and paper passes through rolls of that furnace. And so there are two things. The radiant tube emits heat, paper absorbs heat, right? So there is a radiation heat characteristics associated with the radiant tube, and there is a absorption characteristics associated with the paper. Simultaneous things, right? Now, what is it that you would like? You would want, for maximum or the most efficient mode of working, you would want that the absorption characteristics of paper is very similar to emission characteristics of the radiator. That's when there is best drying of paper. So the radiant tubes that are modeled and are created are based on this premise. So they would tell you, well, paper it's wet, paper has this characteristic, and the radiant hot tube, which is at a high temperature, will have this characteristic to dry up the paper. So what they would look at is, they will try and match these bell curves to the extent they can, so that there is optimum and best utilization of heat emitted by the radiator. So this is the major problem of radiant heat transfer, where they have to match the emission and absorption characteristics of the entities involved. So this bell curve, has to be taken care of. Now, again, see, let's say, have some more patience. I know you might get really heated up at this point of time, and they could thermal breakdown. But one important thing to understand is that if this is a body at temperature, say theta, and the surroundings are at temperature theta naught, and theta is greater than theta naught, theta is greater than theta naught, then there would be simultaneous radiation, which is, and there is absorption, right? Emission as well as absorption would take place. Essentially, the rate at which cooling takes place will be proportional to sigma theta to power 4 minus theta naught to power 4 would be the rate at which cooling will take place, right? Cooling will take place proportional to this, yes or no, right? So this would be like, if A is the area of the surface, then these many watts are being eventually radiated out, and this must be equal to mass into specific heat into d theta dt with a minus sign. Why? Because theta is decreasing with time, it's cooling, right? Now, binomially, you can check that out for yourself, that if theta minus theta naught is small, if the difference between the temperature of the body and the surroundings is small, then we can show that this will be almost proportional to theta minus theta naught. This will almost be proportional to theta minus theta naught. If theta minus theta naught is very small, then d theta dt, this is the rate at which cooling occurs, d theta dt will almost be proportional to theta minus theta naught. if the difference between the body and the surroundings is not very large, then theta minus theta naught, and this essentially is Newton's law of cooling. Newton's law of cooling. He didn't spare anything in maths and physics. See, he's there everywhere. Yeah. So this is the rate of cooling. So essentially, say the surroundings are at temperature theta naught, which is not going to change significantly with time, but theta will change significantly with time, right? And let's say theta minus theta naught is small, then d theta dt essentially would be some minus c at any given instant of time, theta minus theta naught. Let's say theta was initially theta 1, and then after a while it becomes theta 2. Theta was initially theta 1, after a while it becomes theta 2. And I want to find the time the temperature of this body changes from theta 1 to theta 2. So at any given instant of time, this would be d theta dt would be, let's say, minus c times theta minus theta naught, right? And what this would mean is I could integrate this theta by theta minus theta naught is minus c dt at time t equal to say 0, theta was theta 1, at time t equal to 2, theta becomes theta 2. Right? So this will give me theta a function of time. This will give me, let's say, theta 2 to t. This will give me theta a function of time. So I can find out the time it takes for the body to cool from theta 1 to theta 2. If you plug in theta equal to theta 2, you will get the time it takes for it to cool to theta 2. But you don't do all this. This is very ornamental. We just don't do all this. I'll tell you what you should be doing, and that will work in an examination, because in an examination you will not get logarithmic values. It will become horrendous if you do this. In an exam, just very quickly, what you want to do is, say they tell you that the surroundings are at 20 degrees centigrade, and this body is initially, let's say, at say 30 degrees centigrade. And they say the time taken by this body to cool from 30 to 25 degrees. The time it takes for this body to cool from 30 degrees centigrade to 25 degrees centigrade is say 1 minute. Is 1 minute. Find the time it takes for it to cool from 25 degrees centigrade to 22 degrees centigrade. Find the time it takes for the body to cool from 25 degrees centigrade to 22 degrees centigrade. Say they tell you it takes 1 minute for the body to cool from 30 degrees to 25 degrees. Find the time it takes for the body to cool from 25 to 22 degrees. Don't do all this. Although this is right, but shouldn't do this. What you could do is, in this case, what's the total cooling that takes place? 5 degrees in 1 minute. So 5 degrees per minute. 5 degrees per minute is the rate at which this cooling takes place. That must be some constant C into the temperature difference. Now, what's the average temperature of this? 27.5 is the average temperature of this. So what's the average temperature difference between the body and the surrounding? 7.5. See, the average temperature here is 27.5, right? So the average temperature difference is going to be 7.5. So then I say the rate of cooling, 5 degrees in 1 minute, is C into 7.5 is the average temperature difference, right? C I do not know. Okay, that's for this situation. Now come to this. The C will be the same for both the situations, because it's the same body that we are talking about. Now when I talk of this, what is the total cooling? 3 degrees, let's say in time t. 3 by T degrees per minute. 3 by T degrees per minute, right? That must be some constant C. What's the average temperature here? 23.5, right? What's the average temperature difference here? 3.5. Divide this by this and solve for T. That's the time. Now, obviously, many things wrong about this. Because, that's not the average temperature, etc. But tell you something very simple. The temperature that you get, the time that you get out of this and the time that you get out of this in minutes will differ only, if at all, in the second or the third place of decimal. So the error produced by doing this nonsense is very little. So do this. Right? This is wrong, but right. Right? So it makes sense to do this. So that was a very, very quick, brief outing on radiation heat transfer. There are some problems. We'll look into this in the next class. See you then on Sunday.